so here's a third problem with homework 14, and it is by far going to be the longest one because I'm asking you to solve this problem using all three methods that we've learned, and that's vector math, 3-diagram method, using it on bar BC, and the ICR method. And so we see this is called a 4-bar mechanism. And in my class, a senior level class called Mechanisms, ME401, we deal a lot with 4 bars and crank sliders. It's our basic building blocks of mechanisms. And this thing is 2 feet long here, 3 feet long there, and 1.5 feet long here, so we could figure out what the rest of these dimensions are, or what we need. And let's see here. So the crank is moving. This crank here, AB, is moving at 12 radians per second. So counterclockwise. So we want to find the angular velocity of CD using all three of these methods. So let's get started. Okay, so I've written out the problem. And I think the vector math is the one that's going to take me the most amount of time. But let me get some geometry. But that really is an ugly looking little arc right here. Let's try to make that a little prettier. Make the arrowheads look a little better. Oh, okay. Cheat that in there. Okay, so from this thing, we can figure out what theta A is going to be. We know that this is the height of this triangle right here. So we can get theta A is going to be, and that's going to be opposite right there, right? So it's just going to be the arc sine of opposite over hypotenuse, or LCD 1.5 divided by a hypotenuse of 2. And is that like on one of those standard triangles? I don't know. 1.5 and 2 divided, and arc sine. No, it's not 48.59 degrees. All right, that's weird. But okay. Did I do that right? Yeah, I think so. Okay. Sure. So when we do this, what we need to do is find the velocity of B to start with, right? So the velocity of B is going to be equal to the velocity of A plus the velocity of B with respect to A. These are vectors right here. And that means the velocity of A plus, I think I have to go omega. Sorry, does omega go first? I think omega goes first. AB, yes, crossed with R, B with respect to A. All right, it's always good practice to do these things. All right, so we know that omega AB is equal to, it's positive, and it's 12K, right, radians per second. We can find RB with respect to A is going to be equal to 2 feet times the cosine of 48.59. I don't think I need to write I don't even think I needed that bracket. And oh, and by the way, let's see. We need B with respect to A. All right, so when you're going up to B, so this definitely is a positive number. And then its vertical position should be equal to this right there, right? So it should just be plus 1.5. Should be equal to that, 1.5. J. And these are feet right there. So I can get what this actually equals to. Cosine 2 times, and we get to this is 1.323 I plus 1.500 J feet. All right. And we know that's equal to 0. A doesn't move. So we can find the velocity of B is equal to 12. And we can cross this. So we can kind of skip a step. We don't have to rewrite the whole thing out. This times 1.323 K crossed with I, which we know is J, plus 12 times 1.500 K crossed with J, which we know is negative I. So I can flip those back over onto the thing and say 12 times 1.5, which I probably should be able to do in my head, is 18, but it's going to be a negative 18.00 I, and I started to write I first, plus our 12, actually, let's see, I have it in there, 12 times that right there, right? And that's positive. Yes. Okay. So what we want to do when we get done with something like this is make sure that we do a sanity check, right? And this is going to be feet per second. Make a sanity check, all right? So that's up in that direction, right? So it should be negative. It should be negative x direction, and it should be upwards, right? So it should be negative and upwards. All right. So one thing we might want to do is set up this guy right here. We might want to do this link next. Do I want to? I'm going to get to this link right here, and I'm going to find that I don't have enough information. But from this link right in there, so let me do, so this was, this whole thing right here was link AB, right there, right? Link AB. Now we're going to do link CD, but we're going to do like a preliminary version of him, right? We're going to say, we're going to put a pin in it, but it's going to help us in a little bit of a way here in a second. We don't have to do that. We could do the other one to see if we get stopped, and then we're going to, well, I don't know what to do, but then we're going to find this here in a second. So we could take the velocity of C is going to be equal to the velocity of D, use D as the reference, plus omega CD crossed with R C with respect to D, right? We don't know omega CD, but we can write out a space holder for him that's omega CD K. Assume it's positive, right? And we can find RC with respect to D. We can even just write it out. RC with respect to D is just upwards, right? So it's just going to be J, right? So it's just going to be upwards so it's going to be 1.5 J. And it is C with respect to D, so it's looking at C, so it is going upwards. So it's just 1.5 J. And we know that the velocity of D is equal to 0. So we can say the velocity of C, based on this link right here, is going to be omega CD times our 1.5 K crossed with J. And we remember K crossed with J is going to be a negative I, right? We're good with that? Let me double check I did this right. K crossed with J, negative I, right? So we could just write out that the velocity of C is going to be, let's see if we just write it this way. Negative 1.5 omega CD I. and it makes sense that's in the horizontal direction. This thing has to move in the horizontal direction. We could actually use that knowledge later on that we know that C will not be vertical. That's something that we can use later on. But let's continue here. So now let's go with link BC. And so now we know the velocity of B. So let's try to find the velocity of C. All right, so this is the link V. So we say the velocity of C in this one is going to be the velocity of B plus the omega BC crossed with RC with respect to B. Now, once again, I skipped the step where I called this thing the velocity of C with respect to B, all right? But we know that's what this is, right? This is the rotation part. This is the translation. This is the rotation. All right, so we don't know omega BC yet, but we do know that it's going to be some value times RK. And we can find RC with respect to B pretty easy, right? That's just going to be C with respect to B is just looking over in that direction. So it's just going to be a positive 3 feet I. So just 3 I. And these are feet. I should write these feet. So we can find velocity of C is going to be equal to velocity of B, which we already know up here, negative 18, well, I'll make that into an 18, I cheated, I plus 15.87 J plus omega BC times 3 times K crossed with I, which we know is J. And maybe I'll write that thing out again. So I'm going to write negative 18.00 I plus, and I could write this in a couple ways. I'll go ahead and write it out this way right here. I'll go 15.87 plus omega BC times 3 J. Here's a velocity of C, and here's a velocity of C. They have to be equal to each other. So let's equate them. Like so we might call that this is equation 1 maybe right here, and here is equation 2. So 1 and 2 together. That's supposed to be an and symbol. Not a very good and symbol. And that's not even a good and symbol. Let's try a better and symbol. And right there. So we say that omega CD times, no, let me go, negative 1.5 I, it's going to be equal to negative 18.00 I plus 15.87 plus omega BC times 3 times J. Now separate these into two parts, into I and J. So the I says that we have negative 1.5 omega CD is equal to negative 18. Is that true? Let me see something here. I just want to double check. This is a kind of unusual that I could just solve for this one, but I think I can. I think it's just simply because, yeah, I think I can just solve this one if I want to. Yeah. Because this one has to have 0 in the j, so this right here has to equal 0. So I can actually find omega CD is going to be 18 divided by 15, or 1.200 radians per second. It's positive, therefore it's counterclockwise from our convention. In J, and we didn't have to find this, but it's going to help us here in a second, just so you know, so we might as well find it. We're going to say that 0, that's the 0 over here on the side of J, is going to be equal to 15.87 plus omega BC times 3. Therefore, omega BC has to be equal to a negative 15.87 divided by 3, aka negative 5.292. Whoops. I went 15 minutes apparently. That's when my screen goes off, like radians per second. Therefore, that's clockwise. We don't want to write clockwise because there's a negative number there, but that's something, right? So here is what we were aiming for in our solution right there. And you can kind of see the vector approach to this. Something you need to learn how to do is the vector approach to things. But we also want to do the 3-diagram method, right? So I'll do the entirety of a 3-diagram method to see them worked out. And by the way, I don't give, because of the reduced homework, where I only give 2 problems on the short day, and then only 3 problems on the weekend. You might not have enough opportunity to do some, to solve multiple problems, and you really have to really get strong at this. So I'm saying, homework is like the minimum amount of problems that you have to solve. You need to solve many more, so that's why we have practice before exams and that kind of thing. But I would really encourage you to look at different types of problems as well. All right, so we're going to do the 3-diagram method. This is problem 3 continued, and here's the 3-diagram method. And we're going to continue. We're going to need to do some more of these when we do acceleration analysis. We have to do a velocity analysis to do an acceleration analysis. So maybe we will have some more opportunities to practice these problems. I'm sure we will. So the 3-diagram method here. First off, what we do is we start off with just link AB. And this one we don't use the 3-diagram method because this is pure rotation. But let's see, this one is coming down this way right here. And we know that it's got a velocity this direction right there. Velocity of B is coming off that way right here. And maybe I want to write that velocity of B over to the other side. VB is coming that way right here. And we know that this angle right here has to be the same as this angle right there, right? That's just this is the theta A right there that we know is going to be 48.59 degrees. Right, so this is the 48.959 degrees. Stuck it right in there. So the velocity of B is going to be, and this is, let's see, omega AB is omega AB times the length of AB, which is 2 feet. So that was 12 times 2 equals 24. And these are feet per second. All right. And okay, so that was the first part of the velocity. And this actually can be done, we could use this same thing for the instantaneous center of rotation, just so you know when we get to that part. You're going to see that's going to be a pretty easy one. Okay, so now we need a 3-diagram method. So we have to go for link. Let's do the link. Now let's just go with this. Link BC. So this one's horizontal. And I need to draw them 3 times, so I wish I'm gonna make that other one smaller, just to fit it onto there. Let's make this one smaller. Okay. So we say that one's equal right here plus. All right. So we have the velocity right here of VB, which we know is, all right, so I'm going to take this angle of 48.59 degrees. And we know that this velocity over here has to be horizontal. How do we know that? Well, this thing has no choice but to go left and right, right, because of the position that he's in. So what we do is we use this as the reference, and so we put the velocities at both spots. So this is VB, and this is VB, but we only have to write this one out as 48.59 degrees. And then if this is the reference, we're using VB as the reference, and we're trying to find VC, it's either to the left or to the right, we're pretending like we don't know, then we're going to pivot this one right here. We're going to pin him, and we know that he is either going to go this way or that way. So what we're going to do is we're going to pretend that we don't know what direction he's going to go, but we can guess, right? We know this guy has to go horizontally, and this is going up and over to the side. So in order to find what direction, in order to make this go completely horizontally, this one needs to rotate counterclockwise and have a downwards velocity, but I'm going to pretend that we don't know that. And so this right here is the velocity of C with respect to B. And this is the angular velocity of BC. And then this is the length right here of BC, right in there. So what we're going to do is we're going to write out for this spot, right? It's going to be, this is the one that this is the location we're going to write this for. It's going to be equal to VB plus VC with respect to B. You can see that that's the same equation we've been using, right? Velocity of C is equal to the velocity of B, is this guy, plus the velocity of C with respect to B. And by the way, we know the velocity of C with respect to B is going to be omega BC times L BC, right? That's going to be the magnitude of this. So what we do is we write this into the, let's write it in the y direction first from what we see right here. So in the y direction, we're going to have 0 right here for this. For this one right here, we're going to be positive, and we're going to get, okay, the velocity, they're going to get that 24 times the cosine of our 48.59, right? That's the vertical component right here. And then this guy, this is the vertical component, this is entirely the vertical component. It's going to have plus omega BC times LBC, which is 3 feet that we got from the original problem. That's that 3 feet right there. We can see from this that we're going to have simply that we can divide this by 3. So we will find that omega BC, and we notice that it's going to be negative. We chose the incorrect direction. It should have gone the other direction, but I purposely guessed it as positive. So we have 48.59 and times 20. Oh, I'm sorry. I needed to take the cosine of that. Cosine and times 24 and divide by 3. And I get negative 5.292, which remember is the same thing we got right here. Radians per second. And I didn't actually need that, but I will in my ICR method, I believe. Okay. Okay, but now in the x direction, this is the one that I actually need. I'm going to say that the velocity of c, which is the entirety of the velocity of c, it's actually, but it's only the x direction, so I don't need a hat onto it. It's just a magnitude. And we're going to have a negative velocity of b, which is 24.00 times the sine of that angle of 48.59, right? And then there's nothing going on in this one. So we're golden. All right, cool. Velocity of c is just going to be negative 24 times 48.59 sine times. So that should come, it comes out to 18.00 feet per second. Okay, so now we can do link CD. In link CD, is now in pure rotation, and we've just found out that the velocity of c right here, and therefore this must be omega CD right there. Velocity of c is equal to omega CD times the length of CD. So we can find omega CD is equal to velocity of CD over length CD times, or equal to, excuse me. So we get a 18 divided by the length of CD, which is 1.5. Omega CD is 18 divided by 1.5. And we get that's going to be 1.200 radians per second. And that's counterclockwise. And I do believe that's what we found from this vector math method right there. And we have one more to do. Even though I know this is very long, got to get practice doing all three methods. So this is, that was actually page 4, so this is actually page 5. Right. I can fill out the rest of this stuff later. Let's see. There. Okay. So this is 3 continued, with maybe an extra dot to say that we're ending. No, I think I messed that thing up. All right, so now we want to do ICR. And on the ICR method, there's a special thing. Because of these, we will find that the ICR is going to be where the links merge together. And let's see how we can believe that. Right? So we're going to assume probably in this problem right here, we would normally in an ICR, we would do this first, and we would see that we would get that what that angle is going to be. But let's draw link BC down here. See if I can draw him. I'm going to give him plenty of space because I kind of anticipate where this is going. And we know that C can only move left and right because of the orientation of CD. So that means that its ICR, its line of action at C is this way. So a line perpendicular to it goes either up and down. And then we also know from this that we're going to get like a velocity of B that's going in that direction. We also know the angle of this right here is that's the 48.59. I think we found somewhere. Yeah, 48.59. Okay. So the if we take a perpendicular to that velocity, continues up, and we could see where the intersection of the ICR is going to be. Boom. Here's our ICR. So this is actually a relatively easy triangle to do right here, because, well, for one thing, we found out this is this angle. So this is also 48.59 degrees right here. And this is a right triangle. So, and one thing we could do is we could find, oh, there you go. Here is omega, and this is BC, right? So it's because omega BC is the one that's rotating about this. And then we can also see that that must mean, okay, our conclusion is that C has to be in that direction, right there, off of this. So let's find out what that is right here. We know this length right in here is going to be 3 feet across that way. So our R, B with respect to ICR, so RB with respect to ICR is going to be, if we want the hypotenuse, right? So it's going to be, if we were going to get this length right here, it'd be the cosine of times the hypotenuse, but we want the hypotenuse. So we're going to take BC and divide it by the cosine of theta A, right there. Right, so we're going to take 3 feet and divide it by the cosine of 48.59. And we're going to find that we get 4.536 feet. We're also going to want to have this value right here, which is going to be the R of C with respect to ICR. So the RC with respect to ICR. We could do it either way that we want to do. It doesn't really matter. But this would be rise over run to be equal to the tangent of this. So we could we would divide LBC by the tangent of theta A here in this case. We could do it in a bunch of different ways, right? So, but this is, I just thought maybe consistent with the one I just did a second ago, so that's the reason why I chose it. I'm going to double check maybe my thing here, but 48.59 tangent divided, and it should be 2.646 feet. And we could test this thing out right here by saying, I don't know, either way. I could take it and square it, and then I could take 9 and add it and take the square root. No, I didn't do that correctly. All right, so I did something wrong right here. Let me see. I was suspicious that I did something wrong. I see. Tangent would be, yeah, I think I'm going to multiply. I think that's what I need to do here, because it would be the rise. So I'd multiply by the run. That's correct. All right. So hopefully you didn't write down everything I just wrote down if you are one of the people that have been transcribing these things instead of like looking, just doing it yourself and then peeking. So this is going to be LBC run times the tangent of theta A, or 3 times the tangent of 48.59 degrees. 48.59 tangent, and it should be 3 times, so I get 3.402 feet. And let me test this out here. I'll square this length, and then square that length is 9 plus, and take the square root, and I should get 4.536. Yep, okay, I got it. That was my test, just to make sure I got my geometry right. So now I can find my omega BC by taking, well, we'll write out the velocity right here is going to be omega BC times RB with respect to ICR. Therefore, omega BC is equal to VB over RB with respect to ICR. And that's going to be, we assumed we had that, right? So that was the 24 that we had already. And divide by 4.536. So 24, and I get 5.292 radians per second, which is an agreement with all the things we found previously, right? We found 292, 292. We found some vectors. We found, where did we go? Where did we find it? Where did you go? Did I not have to find it? Where did you go? 5292, right there. 5292. Losing it. Okay. So now we need the velocity at C. So the velocity of C is going to be equal to omega BC times the RC with respect to ICR. So that's just going to be equal to 5.292 times my 3.402, and I get 18 feet per second. And now the last thing I have to do for this one, as if I didn't know how to do it already, with this is to say we have 18 velocity of C, and this is the omega CD, and that we know that VC is equal to omega CD times LCD. Therefore, omega CD, the thing we want to get, is velocity of C over LCD. I just did this a second ago. I did it again. Okay, so big deal. Divided by our 1.5 feet, and what we're left with is 1.2 radians per second counterclockwise. So the answer is omega CD, and is as a vector, is equal to 1.20 radians per second counterclockwise. And it was a very long problem, but it was worth it, man. It totally was worth it, because we learned so much out of this. Wow, what a great education you're getting. You should be so happy, you should be excited. Isn't that great? It's awesome. You just think it's too much work. Sorry. I think you learned a lot from it. There you go. How long is this video? 38 minutes.